Thank you. And first, good afternoon, everyone. And first, I would like to thank the organizers for providing me this opportunity to present my work here. So today, I will discuss about our recent work, microscopic and hydrodynamic correlation in one-dimensional hard-dot gas. And this work has been done in collaboration with Seema, which is a graduate student at ICTS, and Professor Anupam Kundu, and available here in this archive. So hard dot is a simple yet non-trivial example in the context of classical integrable system. And here we consider, let's say, n number of hard dots that moving on an infinite line, each of length a and of unit mass. And this restriction says that the two hard dots, they cannot come closer to a distance a. Now for the dynamics, these hard dots, they move ballistically in between two successive collisions, and once they come together, if they collide, their momenta are exchanged. So as their momenta are only exchanged, so all moments of the moment are kind of conserved, and these all are the conserved quantities for different values of alpha. Now, the dynamics here, it's similar to the dynamics for the hard point gas particles, that is in the limit of a equal to 0. So if we see that for two hard point gas particles, if these two hard point gas particles come and if they collide, their momenta are exchanged. But instead of exchanging their momenta or exchanging their velocities, we can also exchange their labels, and we can go to the non-interacting, this kind of non-interacting picture where the particle just passes through, it will not interact. So effectively, we get the dynamics for these two quasi-particle trajectories, for the quasi-particles are for this hard point gas, and these are non-interacting. So similar thing we can also do for the hard dot, and that also been described in the last day's presentation by Professor Anupam Kundu. So here, instead of exchanging their velocities, we can also exchange their labels, and we get the dynamics for the quasi-particles. So here, this red dashed line is a trajectory for one quasi-particle, this black dashed line is a trajectory for another quasi-particles. But here, the quasi-particles are interacting. So if it does not interact, the black one, it follows this dotted line, the red one follows this dotted line, but due to the interaction at each of the collision, we get this kind of displacement over the a distance. So ultimately, we get the interacting quasi-particles. So effectively, one can think of a gas of hard dot as a gas of interacting quasi-particles. Now, this hard dot system has been extensively studied using the generalized hydrodynamic framework, where the hydrodynamics has been written in terms of the phase space density like that. Now this Euler GHD or its correction, it can successfully describe about the evolution for the mean conserved densities, but once we are interested about the correlation or the fluctuation in the system, then this framework is insufficient to account for that, and we need a description for a statistical theory of macroscopic fluctuation. And in my today's presentation, I will describe how the correlation, how to compute the correlation between these between the densities of these quasi-particles at different locations using both the microscopic and the hydrodynamic perspective. Okay, so first to solve the dynamics, in general we map the dynamics of the hard dot to the hard point particle system. So the idea that there is a nice transformation, this is a transformation between these two coordinates, and the idea is that starting from initial configuration for hard dots, in hard dots, let's say between 0 to L, we remove all the inaccessible spaces between the hard dots, and then we go to the configuration of in point particles between 0 to L minus Na. And in general, we follow this prescription. And for the initial condition, we consider the initial condition in the point particle picture. So we consider the point particle positions are first chosen from IID distribution and then ordered and then transformed to the hard dot coordinates like that. And for our case, we choose this distribution such that the density, it varies over the length scale L, where L is the length scale for the inhomogeneity. Now with all this setup, we first focus on computing the correlation of the mass density in the microscopic space-time scale, where the correlation can be defined like that. It's a difference between these two moments minus these individual averages, where we write the empirical mass density like that. Now first at equal time, for equal time this quantity, it is proportional to the joint probability distribution that at time t, one dot be at x and another dot be at y. Now one can compute it using the microscopic calculation. The calculation is simple. Suppose that starting from any initial configuration, this is the configuration of the hard dots at time t, and we place one dot at x, another dot at y, and how we can distribute the other dots. So the calculation is simple, but the exact form that we have obtained, that is kind of a big form, and I'm not going to details for that. Here we present the comparison between the analytical, this formula, with the numerical simulation for one particular value of y. So naturally, we see here that around this region of A, we will not see any kind of correlation, and on both sides, we will see this kind of oscillation, which will be of the order of few A. A is the dot length. So these are all about the microscopic correlation. So what about the hydrodynamic correlation? To study the hydrodynamic correlation, we first define the hydrodynamic density field. So to define that, we have the microscopic mass density, and then if we co-scan it over some space delta x in general we take which will be greater than A is the dot length, and less than L is the length scale for the inhomogeneity. So if we co-scan like that, we get the hydrodynamic density field. And in a similar way, if we perform a systematic code scanning for the microscopic correlation, we will get the hydrodynamic density correlation. And in my presentation or in our work, we obtain this correlation in two different ways. One is using the hydrodynamic field theory, that is commonly known as the ballistic macroscopic fluctuation theory, that has been developed recently by Don, Sasamoto, by these people. And also, for our initial condition, we first compute the microscopic correlation and then we coarse-grain it and obtain the hydrodynamic correlation. And ultimately, we try to compare the BMFT prediction with this one. So, but before going to that, this is how we define the correlation, but one can also write the correlation in this way, that if we take the derivative with respect to lambda, we can obtain this correlation, and this is the exact formula where the averages has been taken over the initial distribution. And first we focus on the equilibrium space-time correlation for the hard dot gas, where the hard dot gas start in a homogeneous density with mass density rho naught. So in this case, to obtain the correlation, we first go to the point particle picture, because once the rod configuration is homogeneous, the point particle configuration will also be inhomogeneous. And in the point particle case, we obtain the density correlation like that, and then we use the coordinate transformation and go to the hard dot case, and we obtain the mass density correlation for hard dots. But this is true for the homogeneous distribution. So what about for the inhomogeneous case? So there we need this ballistic macroscopic fluctuation theory to obtain the correlation for any arbitrary initial density profile having this kind of inhomogeneity length scale L. And the basic idea is that the density fluctuation on Euler spacetime scale or the ballistic spacetime scale are dominated by the initial density fluctuations that are coherently propagated to the current location by the Euler evaluation. And more precisely, it is based on these two basic principles, the hydrodynamic principle and the principle of local relaxation. So this part I am not going into details. And the idea is that in the limit of large L, we can write the probability distribution of the phase space density in some large deviation form where we can identify this action, which will be in terms of the phase space density of the dots. And once we write that, we can write for any observable, we can write it in using this kind of path integral method. And then we approximate the exact calculation with respect to the microscopic probability density by the hydrodynamic probabilities. So once we do that, so recall the expression that we wrote for the hydrodynamic correlation like that. So if we replace this expectation by the expectation over the fields, we can write this correlation expression in the path integral method. So once we can write the correlation in the path integral approach, so then we perform the saddle point approximation in the large L limit, and using the saddle point method, we obtain the correlation like that. We get this kind of scaling form for this correlation, where the scaling function exhibits like that. So now for our case, we first focus on the equal time correlation. So for equal time correlation, interestingly, we see there are two different parts. One is the local equilibrium part, which will be proportional to this delta function, and there is this long range part. This long range part is coming due to this type of coordinate scaling with respect to this parameter L. And for our case, for that initial condition that I have described, for our case, we can explicitly obtain this long range correlation like that. And also, if we go to the homogeneous equilibrium state, it is easy to see that this long range part will vanish and we will recover the short range correlation. Now next, we compare this BMFT prediction. So first we compare it with the microscopic simulation. So we simulate the microscopic dynamics, which are basically these blue stars here, and we see that the BMFT is matching quite well with the numerical simulation. And not only that, we obtain the exact expression for the microscopic correlation, and then we coarse grain it. We perform the coarse graining. Yeah, we perform the coarse graining, and which are the orange Ds, and we see that all are in good agreement. And we have also verified this scaling relation. And in the last, we have also computed this unequal space-time correlation. So that part I'm not going to details. We have the exact expression using BMFT. But here we present the comparison between the BMFT, the simulation, and the microscopic theory, and we see that all are in good agreement. So it basically, so this analytical comparison, it provides a validation of the theoretical assumption that one have assumed for the hydrodynamic field theory. So this is my conclusion of my today's presentation, and thank you.
Any questions?
Very nice, but what do the two peaks mean in the distribution? Yeah. So why do you have these two peaks?
So actually, physical understanding. So basically we have from the if we see from the microscopic perspective. So as I said that. So this is basically the corresponding microscopic correlation. So around the region around x equal to y or x is y plus a, so we will not get any correlation like that. So if we do for different y and then if we get coarse grain, so it's basically that I will get the correlation for one particular value of the this xb, this.
Why is it asymmetric? Okay. Maybe we can discuss. It's very interesting. Okay. Thank you.
The speaker.
Thank you.